right. Okay, so yeah, that's actually, I think that's the first seminar I give on Zoom. Well, let's see how it goes. Well, actually, no, it's not the first, but it's the maybe the first hour long. So I'm going to be talking about superconducting circuit realization of combinatorial gauge symmetry. This is work I've done with Dmitry Green on in particular in the superconducting circuit, and it's closely tied to work we've done with Zicheng Yang on combinatorial gauge symmetry. So this work was actually started in January when I was visiting the Quantum Foundry, of which I'm one of the members. So the broad goal of one of the trusts in the Foundry is actually to build topological phase in engineered structures. And the first slide pretty much give away what the structure is. It is a collection of superconducting wires. They're connected in a certain way that, of course, I'll discuss in much more detail, but I just wanted to flash the device, from the get-go and state the goal. Now, topological phase in superconducting circuits has a long history. So I list here some of the prior art, which is mostly due to Yoffie and Benoit Dussault and Feigelman in a series of papers that explore and the ways to realize a Z2 gauge theory. Now, there is also the last one that I list here, Fowler and company. This is a different approach that they build arrays of Josephson junctions and using a gate model to try to construct via evolution and measurement, enforce the constraints of a surface code. Now, the one thing that I want to stress that's the difference of our approach is that our approach, especially in comparison with the approaches of the other efforts to build a Z2 gauge theory, is that it's not perturbative. It's based on a symmetry that I'll argue is exact, and it's there for any value of the coupling. And the existence of the symmetry is crucial to make sure that all the effects we see are not very, very small, and you have to keep couplings in a regime that at the end of the day your gaps are going to be tiny. So this the symmetry that we're going to base on is this combinatorial gauge symmetry that we explain what is it and why do we care. So let me go in steps. So the first step is to ask a simple question. What symmetries preserve commutation relations for a collection of n spins? So n separate spins. What can you do? Well, maybe let's compare this to the simpler case of n fermions or bosons, which we're much more familiar. So there you can do single particle unitary transformations that will preserve, in the case of fermions, the anti-commutation relations, in the case of bosons, the commutation relations. And any unitary will do it. Now, these unitaries means that you're making superpositions of fermions at different sites or different fermions, right? A simple example is if you just have two fermions, you can make the symmetric and anti-symmetric linear combinations. And this is a simple example of a unitary transformation. So all the anti-commutation relations are preserved. Now, suppose you try to do something that you shouldn't really do, which is try to make linear combinations of spin operators. This is really doomed to fail. So here's an example. Just suppose that you take the sum and the difference of two spins. And if you check what happens to the commutation and anti-commutation relations of the new variables, they will not satisfy the same algebra, okay? And one shouldn't expect this. So then the question is, what else, what it is that we can do? So if you look at more broadly what transformations are allowed, so now supposing instead of thinking about single particle transformations, let's look at the ones that really work. You could take a transformation that rotates in the many-body space. So if you have n spins, you're going to have 2 to the n states, and the unitaries are going to belong to SU2 to the n, which is a very large group. So in general, if you take an SU2n rotation, your spins will transform, and this transformation would preserve all the commutation relations, right? But your transformed objects that actually satisfy those relations are much more complicated. They don't have just like the one-body terms. Like it's not just like a rotation. This guy alone here is the counterpart of the single particle transformation that we use for fermions and bosons. But he has all the other terms in the algebra, right? It's a non-commutative algebra. So you're going to get strings of 2 sigmas, 3 sigmas, etc. So what we really would like is not to have these guys. So that's what's difficult. Well, there is one case that's trivial and we can do, is if you only rotate each spin separately, don't try to mix them. That would work. You just rotate them even by different angles. That will preserve the algebra. But then that's too trivial. So what's the next simplest thing, but it's non-trivial? Now, suppose you have here 4 spins. You can rotate them, but the next thing you can do that would preserve if you just relabel them, or you permute them. That's a transformation that will preserve the commutation relations, because you're just, you're just exchanging the spins, but you're exchanging the whole thing together. You're not mixing them. So these transformations, they are monomial transformations. A monomial is a variant of a permutation. So here you have, like in the example, 4 spins that you can first transform them with SU3 and then permute. The transformation of the components of all the 4 spins, and these guys are vectors, so you can think about this also as a vector with 12 components where you have all the components of the spin. But this matrix is always of the form of, it's up to the fact that the G's are not identities. It looks like a permutation. So these is the definition of monomial. Monomial is a matrix that has only one non-zero element in each row or column, just like a permutation. But these elements don't have to be just one. They can be an element of a group. In this case here, SO3 for the spin rotations. And this transformation, these monomial transformations, will preserve the commutation relations between the spins. Now, this is the first step. Like when we look for a symmetry, well, it has to be a symmetry of a Hamiltonian that we haven't written yet. But in the, even more fundamental than being a symmetry of the Hamiltonian it has to preserve the algebra of your operators, and these ones do. Now, the monomial transformations, you can always write them as a semi-direct or Ritz product of 2 groups. One is going to be the group of rotations of these spins, and the other is the group of permutations. Let me give a simple example. Yeah, junk call. Sorry about that. Things that don't happen when you're giving a real seminar live. So let me give a simple example of monomial transformation. And this is, it's a really simple example, but it contains all the elements of them. these transformations. So suppose you're handed in, or we have 4 pairs of shoes, different colors, but each pair has a left and a right shoe. And now let's apply these monomial transformations. It has 2 pieces, right? It has the group G, which in this case, maybe the only transformation it can really make is like, switch left and right of shoes, right? That's a flip, right? And if you flip again, you get it back. So it's a Z2 transformation. And then you can permute your pairs of shoes, okay? Now, one property of this transformation, as done in this way, is that you may not like the color of your shoes, the ones that you end up with, but you're guaranteed that they're going to be both of the same color and that you're going to have a left and a right shoe. So the simple example captures what it is in these monomial transformations that we're going to apply to spins and fermions, bosons, phase fields, and everything. Now, let me give an application. And this was the original work where we found these symmetries, work done with Dimitri Green and Zicheng Yang. So here we're going to realize a Z2 lattice gauge theory with only 2 body interactions. So many of you are familiar with the Tori code. So the Tori code is an example of a Z2 gauge theory. It's exactly solvable, but it contains 4 spin interactions. Now we're going to obtain the same Z2 gauge symmetry within a Hamiltonian that has only 2 body interactions. Now, in the Z2 symmetry, you have the symmetry, which is a local symmetry, consists of taking any loop, and here I didn't close it because the lattice is small, but you imagine a closed loop where you visit a whole bunch of links, and you're going to flip these links, and this operation here, depicted by the red string, commutes with the Hamiltonian. So we're going to implement this symmetry by looking at each star at a time, and these stars contain gauge spins, the ones in green, and matter spins that we label in blue. Okay, so the Hamiltonian of this model only couples the gauge spins to the matter spins. And the coupling is very regular. You couple everybody antiferromagnetically with the exception of one, the closest, if I think about it in this way, I put these 4 guys like this. The matter spin that's closer to the gauge spin, it gets an antiferromagnetic coupling. So the matrix of couplings is this Hadamard matrix. And the Hadamard matrix has the following properties. If you take the dot product of all elements are plus or minus 1 here. And if you take the dot product of any row with another, you get 0, or any column with another, you get 0. So these are orthogonal discrete factors. These matrices are used, for example, for the discrete version of Fourier transform. Now, if the couplings are like this, okay, you have the following symmetry. If you flip the gauge spins, okay, so this is the counterpart of flipping your left and right shoes, okay, the little arrows. You flip things and you permute them with the exchange, and this Hamiltonian would be invariant, okay, because of the properties of this Hadamard matrix. Now, we will consider only flips on the sigma spins, because these sigma spins are shared with they couple to other matter spins in a different lattice point, and we don't want to exchange. We don't want to mix this, have complicated operations here. But the matter spins, you can permute them. And when they say permute them, you're not physically moving one spin in exchange with another. You think about this like a swap gate, like you're swapping the quantum state. Now, mathematically, this symmetry associated with this matrix of couplings is nothing but this Hadamard automorphism. It's a property of this matrix that it is invariant under left and right multiplication by exactly monomial matrices. Okay. So in this case, this monomial matrix here, which is diagonal, so it just flips things but don't permute them, implements the transformations on the sigma spins. And this one that flips, here's the minus sign, and permutes the mu spins is associated with matter spins. So as long as the matrix of couplings, if you choose it to be a Hadamard matrix, and it has this automorphism via monomial matrices, we're going to generate these transformations here as transformations of the Hamiltonian. Another way to think about this is that you can always invert this. If you give me an R matrix, I can always find an L matrix via this transformation, right? That transforms monomials into monomials. So when we write down the gauge transformation, we're just gonna, visit links in the lattice and decide what to flip, and that will tell us what is the associated transformation in the matter spins. So we just argued that if you have Hadamard couplings, this part of the Hamiltonian is invariant under this transformation. What about the transverse field parts, if you want to give the model some quantum dynamics? Well, the flips that we implemented, you can implement that via rotations around the x-axis by pi. So a rotation of pi around the x-axis will commute with the, it's a rotation with both mu's and the sigma. So it commutes with these terms. Now the permutation. So if you want the Hamiltonian to be invariant under permutations, you want all the matter spins sitting on a site to have the same transverse field gamma. So, of course, if all the gammas and all the gamma tildes are the same everywhere for all sites, as written here, it's clear that permutations will not affect it. But the symmetry is actually more general because you can actually disorder the gammas on the gauge sites because you're not using permutations in the gauge sites. In the matter sites, they can actually be different in different sites as long as the four couplings on the same site are the same. So the symmetry is actually much more forgiving than just taking constant couplings. But the bottom line is that this Hamiltonian is invariant under these combined symmetries. Now, to make connection with something that's more familiar, suppose you take this Hamiltonian in the limit where the transverse field is very large, much larger than J, and forget about the couplings on the gauge spins. So let's just apply a large transverse field here. So effectively, if you freeze the gauge spins in a configuration, this is just a Hamiltonian of spins on a magnetic field. Okay? So there is a magnetic field in the z direction for the mu, z component of the mu, and the one in the x direction for the x component. So we can solve this problem exactly. You get the two eigenvalues plus or minus the square root of the sum of the fields. And here, if you expand this thing to all orders, because you basically can, because the algebra of the sigma squares, they square to 1, the w's as written, they square to 1. So you can show that there are some coefficients that you have to calculate here, but this is all you get, a constant and a four-body term. So this is basically implementing in this one particular limit the same term that you have in the toric code, a product of four spins around the star. And there it's clear that you have the Z2 symmetry. And which Z2 symmetry is that? Here, if you go around the plaquette and you flip these gauge spins and you do the prescribed dance of the matter spins, right? So you flip and you permute. Remember the shoes, right? So you just have to do the right dance here. Then this operator will commute with the Hamiltonian, because it will commute with the W term, it will commute with the transverse fields. So you can write an operator, this plaquette operator, and it has to be a closed loop, because as you apply two things here, well, you have to flip everything back to have the symmetry. The symmetry requires that you flip two spins in each little cluster. So you have these closed little loops. And out of these closed little loops, you can construct bigger loops. And all these guys would commute with your Hamiltonian. Both closed strings and winding strings if you put the system on the torus. So this means that you have a Z2 gauge theory, but only using two-body interactions. So this system actually admits quantum spin liquid ground state once you turn on the, well, you need the transverse field to give the quantum dynamics. But it will be the same topological phase as the toric code, which it can be made even more explicit. The connection is if, now suppose if you put these matter spins on the centers of, on the sides, but you put some other matter spins, call them tau, at the center of the plaquettes. So if you can write both ZZ and XX interaction, you put them use the same W matrix. So basically, this is the guy that when you take gamma to be very large, you generate the 4 spin interaction around the star. And this one would do exactly the same thing, generating a 4 spin interaction on the plaquette. So the toric code is just a limit of gamma very, very large compared to J. But the Z2 symmetry for, following loops around plaquettes and then loops in the dual lattice as well, you will have these Z2, both of them. So you have both the electric and magnetic loops. So in short, what we have here, this Hamiltonian will have a topological phase. It has the toric code as one of its limit, but it was designed starting with the symmetry. So instead of like, and this you can think about a design principle, because often we want to write frustrated Hamiltonians to build spin liquids. And so you write something that's frustrated classically, and you, in the hope that when you turn on quantum mechanics, things are gonna, you're not gonna order. In this case, it's different. We start with a Hamiltonian that has the desired symmetry, okay, at all values of the coupling. So you're not gonna lose the symmetry, right? And so it's there from the get-go. Okay? So there is a design principle behind the choice of couplings. Okay, so this highlights the importance of the symmetry, but now we want to go back to this question about actually engineering things in devices that you can build in the lab that are part of current and going experimental efforts. So let's consider the following superconducting circuit. And now that we've looked at the spin model, these things are going to become more familiar. For example, these, so the superconducting circuit consists of the waffles, okay, and wires that, so the waffles have vertical and horizontal wires. The vertical wires are going to be our matter degrees of freedom, and the horizontal wires on the waffle will be the gauge degrees of freedom. So the gauge degrees of freedom, they have to connect neighboring waffles. So for example, this guy connects them in this direction, the theta 1, the theta 3, to the, the guy, the other neighbor. And up above and below, you also have your wires, right? And it's not, it's simple. You just bend your wire here, right? So this geometry here, you can think about, if you just put these wires, they actually have all the same length. The gauge wires and the matter wires also have the same length. And the coupling, we will need the same W matrix. But here the coupling is through Josephson coupling. So that W matrix that has -1s in the diagonal and +1s in the off diagonal effectively just consists of having Josephson couplings with phase 0 in the black crosses here. And in the white crosses around the diagonal, you want a pi junction. You want a pi phase shift when you write your cosine. So alternative, either you put your minus here, or you can think about this as, forget about the W and you put the phase. That when they're, on the diagonal, the cosine is cosine of phi minus theta minus pi, the pi phase shift. So this is how you would implement in the Josephson junction array. And the kinetic term is given by the charging energies. Okay, so you have the capacitance of the matter wires and the capacitance of the gauge wires. And these wires don't have to be the same size. So these capacitances will depend on the size of your structure. Now, where's the combinatorial symmetry for the circuit? So let me just rewrite the Hamiltonian in terms of the phase shifts here, right? So I just re-expand the cosine, and of course I forgot a factor of 2 here. But then this is actually a particular case of something much more general. You could just write, this is a Hamiltonian that involves 2 operators, A and B. The A's live on the kind of the matter degrees of freedom, and the B's are the gauge degrees of freedom. And you can write this very generically. These A's and B's could be bosons, fermions, spins, phases. So in the case when they're phase operators, just like here. So what is the symmetry? They will flip. They will exchange your left and right shoe. Well, the flip operation can be implemented by, Zoom just put the bar right on top where I want to put the pointer. Give me a second. Let me move the bar. So this is implemented by the charge operators. So the pi phase shift, because okay, you're not flipping all the matter wires, just the ones that you want. So the ones that you want to flip the sign or give it a pi phase shift, you will use this unitary e to the I pi q. And this unitary would kick your phase by pi. Okay. And it's generated by the charge operator on the matter wire. And similar, if you want to flip or give the gauge wire phase pi, you use the charge operator to generate those translations. Now, these operators, since they're expressed in terms of the charges and the kinetic term of the Hamiltonian is the charging energy, it will naturally commute with the charging part of the Hamiltonian. So in short, you will have the same symmetry as we had in this spin model. So in the language of the superconducting circuit, right, the transformation that we implement is, suppose you kick this phase theta 1 and theta 2 by pi. So you have a piece of a loop here. It will flip this phase and give it a kick of pi. So this is shown here. Theta 1 goes to theta 1 plus pi, theta 2 to theta 2 plus pi. So this is compensated in such a way that the W, this guy, is invariant. If you flip the phases of 3 and 4, if you kick it by pi, and if you now permute the phases of 1 and 2 and of 3 and 4. Okay, so again, similar to the shoes, you do your dance, you do your flips and permutations. And the configuration with these phases and these phases has exactly the same energy here. And in these operations, the operation of flipping commutes with this part of the Hamiltonian. And because of the capacitance of the wires, of the matter wires are the same, if they have the same length, it will also commute with the permutation part of the operation. Okay, so we know that, so let me just go back. For any values of J and C's, this Hamiltonian has the symmetry. And I could start applying the symmetry and follow loops, you know, of any size, and I have the symmetry in the Hamiltonian. But now let's try to understand the ground states of these types of Hamiltonians, and that's actually quite rich. So let's focus on the potential energy first. And let's ask, well, where's the minima of that potential energy? Now, if all the W's were positive here, so if you just have the, you know, the usual couplings that you want to make all phases equal, what you're going to end up is with an XY model. And so, okay, you obtain all the phases with one order. So what happens when you have this W instead? Well, the minimum is such that the phases on the links, and here's an example. You have the phases of the gauge wires and the matter wires, and the minima are such that the phases are equal pairwise. So for example, in this wire, in this gauge wire, you will have some phase beta, and there will be another wire with a phase beta. In two, they will have phase alpha. Alpha and beta can be whatever. As long as they are pairwise equal, that's the minimum of this potential. So, you know, here are three configurations, right? You know, the blue link, you can either follow straight, turn down, or turn up. But all of these configurations will have exactly the same energy for whatever value of alpha and beta. And here we see the elements of a theory of loops, right? Because you're implementing some local constraint that you know, the forming pieces of loops. We will get to there in a second. But let me mention that the little plaquette operation, what it does is that it shifts the angles by pi. Okay, it gives a kick. So when we say that these angles are equal pairwise, keep in mind that they're equal pairwise mod pi, not mod 2 pi. And the difference between mod 2 pi and mod pi is exactly the Z2 that will make this, you know, this theory of Z2 topological state. So let's consider, since the potential energy already is so interesting, let's kill the kinetic energy and study first the classical model. Okay, so we're going to send the capacitance to infinity first, so we get some intuition on what's going on. Because you have these phases that are equal pairwise, once you tile the whole lattice, what you're going to get is a theory of loops. So every, you know, you can follow, it's a fully packed loop model, meaning that every link in the lattice gets a piece of a loop. And the color here, the color assignment is to indicate the phase. So for example, these guys in blue have a phase beta, mod pi again, And the red one here is a phase alpha, phase gamma. And whatever way that you tile the plane with loops, it's a ground state. So the ground state is massively degenerate. Not only it's degenerate in the way that you're going to tile it with the loops, but also whichever phase that you decide to put in the loop. On top of that, you have these Z2 loops because you can come here, for example, around this plaquette, and I can kick all these angles by pi, okay? So in terms of the physical degrees of freedom in the superconductor, there's a different, you kick by pi, you can tell. But in the definition of, we separate those physical phases into the product of these U1 loops defined mod pi, and whether or not you apply these loop operations. That basically means that the loop partition function of at zero temperature, okay? So at zero temperature, you're going to just enforce the minima of all the vertices. You're going to satisfy the condition that you have two bonds of the same color with the same angle. And your partition function factorized in the product of the Z2 loops and the U1. And the U1 here, there's a subtlety that it's U1 mod Z2, which is isomorphic to U1. So you don't have to worry too much about this in computing the partition function. It just gives you a factor of 2 in the fugacity. But it's important to not to double count things. So let's focus on the partition function for the U1 loops. So the partition function is given by all loop covering. So going back here, you have to sum over all possible ways that you're going to cover the lattice with loops that, closed loops. And they are weighted by a fugacity. So the fugacity is basically the number of colors that you can have. And then there's an interesting paper by Chase, Periodico, and Stengel on the ZD model, where D is the number of colors. Now, one thing that's very peculiar to our model is that because we have a continuous symmetry, you basically have an infinite number of colors. And then this simplifies the analysis, because if you have an infinite number of colors, then you could ask, what are the configurations, what are the loop coverings that will get the largest weight? Well, if you send lambda to infinity, you actually want coverings that will maximize the number of loops. And here it goes. So the limit of infinitely many colors, you maximize the weights by having the maximum number of loops that scales as L squared. So you form a loop crystal where you have loops at a checkerboard configuration of loops. And within each of these tiny plaquettes, the phase can fluctuate, right? It can be anything you want, and those are states with equal weights. So in this loop crystal, it's at the same time it's a loop crystal, it's a spin liquid. Because if I look at the phase angle here, for any link and any other link that's not even too far away, like this link and this link, they sit at different loops, and these loops can fluctuate independently. This angle can be any alpha, this angle can be any beta. So there's no correlation between these spins. So the U1 part, the correlation length is basically lattice constant. So then you go back and you say, okay, well, we have this loop crystal, but what about the Z2? Well, the Z2, there's nothing that fixes its sizes. So you can basically write any loop here of any size, and it's weighted in the same way in this partition function. So you have an example of Z2 classical spin liquid because of the surviving Z2. So that is the classical piece of the model. So the next question is, okay, let's bring quantum fluctuations back. So we're going to bring it first by taking the matter capacitance to be very small, and we're going to keep the gauge capacitance large, right? Because this model already allows you to introduce strong quantum fluctuations in one of the components. And because the symmetry was exact for all values of the capacitance, the combinatorial gauge symmetry is present in this model here. So in this model, if you make the capacitance of the matter wires very small, it means that you favor two neighboring charging energies, say n and n plus 1. And you project everything else out. Now, I'm going to bring this point back that the symmetry is exact for all values of coupling. So it's not the fact that we're projecting states out that gives us the symmetry. The symmetry was there from the beginning, and it's there, and you see it's not lost. But what this does is just change the nature of the degrees of freedom. Okay? So here, because you project out other states, you have to substitute your charge phase kicking operators generated by the charge by some two-level system. You have a mu plus and mu minus. You can just kick it from n to n plus 1 and back. Okay. So you substitute the e to the I plus or minus I phi's by the mu plus and minus in this Hamiltonian. And if you have a gate voltage that bias it not to be exactly in the middle here, but there's some excess, you will have a bias term for mu z, and everything else is the same. Right? This is the charging energy for the gauge wires and the phases. And we can do, like in the case of the Turing code, if you that we did, like if you kill this guy for now, like send CG to infinity, then you can actually diagonalize this Hamiltonian exactly, these two pieces, right? Just go back here. Why? Because now the matter wires are independent, and I can just think about this as effectively a 2x2 matrix for fixed theta i's. And I can diagonalize this matrix. There are two eigenvalues, plus and minus. And I'll always take the minus for all the index ends. And that will give us the low energy manifold, which is basically this expression here, very similar to what we had in getting the toric code limit of that spin model. And one can check that even though you have the square root here, it said it looks, doesn't look like so pretty, but you still have exactly the same, minima of this potential as we had before. It's just that before the thetas were slave to the phi's, and now instead there's no more phi's. We integrated them out, right? So you're still going to have a theory of loops, okay? And you're still going to have your plaquette operators, which now it becomes much easier to write. They're just product of the charge operators around the plaquette. So let's look at the quantum critical theory now that, or at least we integrated out the matter spins, we left with the gauge spins, and now we can take that capacitance not to be infinite, but large. So the inverse of the capacitance will be one of the axes that we're gonna push the system, and the other one is the deviations from Hadamard, because so far we've been sitting in this Hadamard point. So let's look at the deviations from Hadamard first. So in the Hadamard case, we had -1 in the diagonal. Now suppose that you change them by these phases of eta. Okay. Now the W matrix doesn't have to be Hermitian, because if you go back to the way we write the phases, so far we all they were always Hermitian, but these are just phases. So you can write the coupling between phi's and theta's, right, through the Josephson junction plus the complex conjugate. So this eta here is basically the phase of the coupling of the the e to the I phi or e to the I. Imagine like phi minus theta plus some phase, and the phase is this eta. In the way we write, we put a minus sign, so the eta equals 0 would be the case we discussed so far. Now, if you perturb the matrix and you expand for small eta, what you get is that old Hamiltonian that enforces loops, but you acquire some XY magnetic coupling, and this XY would tend to order. This is a two-body term. So to be contrasted with this guy that wants the theory of loops. So of course, if you start pushing this guy too far out, in particular when eta equals pi or minus pi, you just have ferromagnetic couplings. So you would expect that your ground state would be an XY ordered state, not a spin liquid. So that's what we would expect in this direction. Now, what about the other axis, the capacitance? The capacitance we can just include in the Lagrangian, right? The capacitance term comes in with a theta I dot square. So it penalizes fluctuations around the time direction. Now you can understand this model by thinking, okay, it's 2 plus 1 dimensional quantum. You can map it to a 3-dimensional classical model, especially if you forget about this this important term here to give you the topological state. But if you just look at the first two terms, it's the familiar XY model in 2 plus 1 dimensions, which you can understand, the phase boundaries, when it orders, when it doesn't, by rescaling the couplings, and you can study the 3D classical XY model with a coupling which is the square root of the J times the capacitance. And when this coupling is large enough, the system will order, will have XY order. And if this coupling is small, the system will not order magnetically. So you see here that the capacitance helps that a large capacitance will help you order as soon as you have a non-zero eta. But if the capacitance becomes small, or CG inverse becomes large, you will tend to disorder. So if you use this expression to determine the phase boundary of the XY ordered part, you basically get the J. The coupling follows this cosine function here, or 1 minus cosine. So you see that at the Hadamard point, you have no ferromagnetic coupling that will give you XY order. But if you deviate from it, then you're going to get order, because especially, problem with these getting one by one is that if you go back, you have to rebuild. So even if the J is small, if the capacitance is large, if you go classical, it will order, right? And this is what we're seeing here. But then if you decrease the capacitance, you're going to push out of the XY order. And in particular, at the Hadamard point, there is no J. So it's easy to disorder. And if you increase the capacitance here, you add quantum fluctuations. So the phase diagram of this thing is, if you kill the XY order, you will get near this point here, where you have the Hadamard symmetry, the loops, you will have Z2 quantum topological order now. Okay, so you're going to get this quantum spin liquid out of your superconducting array. So let's go back and look at this guy. then compare. This is the presence of this Z2 topological order. It can happen in these three XY-like models. And one example is what Subir Sachdev has in this Reports of Progress in Physics, where among many models, it considers these 3DXY that has an additional four-body interaction that's labeled by this K here. So K controls that. So if you look at the phase diagram of that model, let me first discuss it. If you didn't have this K, and the K is the counterpart of, you can think about the K. It's not as simple, but it's related to the fact that by imposing these constraints between the links, you want to get something that looks like a loop theory. So that's how I would interpret within our language. So if K is 0, you just have XY. And with XY, you only have XY no order or XY order, right? But then if you push it away, if you add more ingredients to your XY model, then you can have a Z2 topological phase. And of course, if you increase J too much, you're gonna order it again. So the translation table between this phase diagram and our phase diagram that comes from this microscopic superconducting array is that, okay, here, this is the blue phase. And if you push down the blue phase to disorder the blue phase, you go to the pink phase, and the pink phase is the Z2 topological order. Now, one thing to stress is that in our case, we know that we have this Z2 symmetry from the get-go. That's the combinatorial gauge symmetry. So if you're sitting along this axis, you have it for any value of G. So it's not emergent, it's there from the beginning, okay? And well, another observation, of course, this here we get with two-body interactions only, okay? So basically this model one can build, right? So now let's go to the extreme quantum limit. The extreme quantum limit is the limit where both capacitances are small. So now you can take the limit where both the matter and gauge wires are two-level systems. And in this case, you get this thing that we call the WXY model, okay? Yeah, some of these things are, some of these coincidences are really interesting. We call these things W, and it happens that, there's a W in an XY model. And the W is coming from the couplings, the combination of ferromagnetic and antiferromagnetic couplings that frustrate the model so that, but it's not just any frustration. And this, again, I want to stress. It's often the case that we put frustration in a spin model because we want to prevent the system to order. For example, if you can take kind of a classical ice model, and then you want to turn some quantum mechanics and just hope that the quantum mechanics will not lead to order, right? Or it happens in many other examples that usually it's a good recipe to try to get a spin liquid is to get something that is frustrated. But this is not enough. Here, the design principle is that we want to have this frustration, but we want to have the frustration in such a way that you have a symmetry from the beginning. So if you have a Z2 gauge symmetry in this model for any value of coupling, right? Well, here it's actually simple because there's only one coupling. But if you have it as a symmetry of the Hamiltonian, we are already set up the system along a trajectory that that's promising. You have the symmetry that if you want to realize a Z2 quantum spin liquid, and you have the symmetry there from the beginning. Which is not trivial, right, to have it, especially if you only have the two-body interaction. But we do. So then what we expect for this XY model from what we studied in the both in the classical version or in the I wouldn't call semi-quantum, but limit when we had small capacitance in the matter wires, like, and then we turned on slowly the capacitance in the gauge wires. Then we got this phase diagram with a topological phase. That we would expect that if you crank up that inverse capacitor or decrease the capacitance of the gauge wires, then you still have this topological phase. But now, that quantum spin liquid, if it exists in this model, there is only one energy scale in the problem. So you're going to have a very large gap of order J. And, for applications on, if you want to build a topological qubit, it's not just enough that, you study some phase diagram and you're happy you found a topological phase. Well, if your gap is really small, right? If it's perturbative in, say, the fourth order in something, and your J is of, some scale, 200, 300, 400 millikelvin, and you have a gap that's 4 orders of magnitude smaller than that, it's useless that you have a quantum spin liquid, right? Maybe it's good to write theory papers, but you're not going to use it to build a topological qubit. So a good route is to find a model that has a very large gap, and this is promising because there's only one energy scale in the problem. Now, of course, this is hard to establish because of those antiferromagnetic couplings. This model has a sign problem. Okay, so it's hard to study. Maybe we can study with the MRG, but yeah, and it has many spins per unit cell. So EG, it's very difficult. So a student of under Senvei Kaishin Wu has played a bit with the small systems, and there is some evidence, especially if you add magnetic fields in the z direction, which preserve the combinatorial gauge symmetry, that you can use to kind of change the magnetization sector that you study this model. And the systems are too small for us to like stick our necks out, but it looks like there are peaks in the fidelity susceptibility suggesting there is a transition from something to something, and we think that there is a region where this thing is a spin liquid. But of course, to say anything more, we would have to do the MRG. So let me conclude. So I presented this notion of combinatorial gauge symmetry that preserves commutation relations for spins, and that's important. That's the new element, right? The spins and phases. Bosons and fermions, we have plenty of things we can do. So this thing preserves this for spins, bosons, fermions, phases, shoes, etc. And we have realizations of a Z2 topological order with only two-body interactions, both in spin systems and now in superconducting circuits, which, in the spin system, you have to find a system that has those interactions. But in the superconducting circuit, you can, hopefully we can just design it, and the model is just, it's quite rich, even in the classical limit with this theory of loops. So certainly there's room for a lot of fun in the superconducting circuits. So thank you.
Thank you very much, Claudio, for this very nice talk. Now we are opening for questions. So if you have questions, you can raise your hand or send your question in the chat box. If you are following us on the YouTube live, you can also send your question there. So I see a question from Chamon. I asked you to unmute.
Shall I unmute him?
Yeah, I think I'm already unmuted. Yeah.
Okay, thank you.
Oh, hi, Claudio.
Hey, Zicheng, how are you?
Yeah, that was very interesting. So actually, I have a question about the excitations in this model. Um, in particular, the magnetic charge. I mean, the electric charge in this model, I can imagine that if you're, for example, if you just flip the phase um, of the associated with the gauge, field theta that you call, then I can probably violate two constraint at the two vertices, and I create an electric charge. But what about the magnetic flux?
Okay, so I think this is similar to the model we looked in that this guy is enforcing is basically enforcing the star,
Right.
Mm-hmm. And then you rely on the rest of the quantum fluctuations to give you the quantum dynamics.
Mm-hmm.
So
yeah, that's why I'm having a bit trouble of seeing that. I mean, because the quantum fluctuation is more complicated in this case.
Yeah, that is true. It's more complicated because, well, in the other case, it's discrete, right? So when you apply the transverse field, you just flip things and you generate, for example, you generate a plaquette term, mm-hmm. right? So in this case, okay, there is the counterpart of kind of integrating out the matter degrees of freedom, right? So you back, this guy is the counterpart of this the star constraint. It's mm-hmm. just that it's just there's not as a clear picture in terms of spins, right? Because here these phases can be anything, right? So it's not like
yeah, like in Sabir's model, there I mean the magnetic charges are vortices, but here I think it's, I'm not sure whether it's because I don't see immediately.
Yeah, you could.
Because I think there they only condense even vortices and then expel odd vortices, and these odd vortices they carry Z2 flux, but mm-hmm. Yeah, I don't see immediately.
Yeah, I think the analog here, it's the same half or double vortice, right? Mm-hmm. That the phases in the superconductor, in these two loops, right? When you write U1, it's just okay, it just happens that U1 mod Z2 is isomorphic to U1. Mm-hmm. But I think it's the difference that the phases, when you want to factorize, they're only defined mod pi, not mod 2 pi. Mm-hmm. But in the superconductor, the physical phases are defined mod 2 pi. Mm-hmm. So somehow you have to encode that information, and it and the information that okay. So in your model here, whenever we draw a loop, right, these phases are only defined mod pi.
Right.
But you can do any transformation that will flip these phases mod 2 pi. Mm-hmm. So I think that the excitations are going to be, I think it's exactly the same. It's like this issue about half vortex, even or odd condensation. It's all tied to the fact that the phases are defined mod pi, not 2 pi. So I have to think about the dictionary more precisely, but I think at the end of the day, that's the root of the root of the Z2 is just this thing. Is that mm-hmm. phase mod pi plus some degree of freedom that you can think about. If that phase you're going to add 0 or you're going to add pi, so that you go back to the 0 to 2 pi.
I see. Okay, thanks.
We have a question from Tarek. We know that gauge fields are force carriers. What kind of force do the gauge fields carry in your model?
Well, usually a continuous a gapless gauge field will carry force, right? Just U on electromagnetism. Not in the topological theory, right? Not in the Z2 that's gapped. So the answer is that it's different if you have a gapless gauge theory or if you have a gapped gauge theory. So in electromagnetism, you have your actions at F square, right? F mu nu square. So there you're going to have your Coulomb law. But if you have something like, for example, Chern-Simons theory, there, it's just pure gauge. And so the answer is that, yeah, there will not be any force here if, in these gapped gauge theories.
The question continues, is it possible to have symmetry breaking in your theory?
So the symmetry breaking is the XY phase, right? So here. So this is a symmetry broken phase. So that's the order. And in here, it's disordered. So that's the very definition of the spin liquid, right? You don't want to break a symmetry here. So there is order, but that's not where we want to look. We want to look here. That's where the interesting things are.
Any other question? Maybe I got a question. You mentioned that because of you would like to check out the simulations with larger system sizes using the MRG. Would it be required for you to kind of reshape your geometry because maybe you could have a long range order?
Oh, so let me go back to that. So this guy, oops, too far. Yeah, so for that, we will have to put this on a tube, right? And we have, basically we have 6 pins per unit cell, right? So when you say reshaping was thinking, okay, well, we're gonna have to put this guy on a tube and then you can take a very long tube. But the size of the system will be limited by the radius of the tube. But when you say prevent order, well, I think it would start with this model with only the interactions that
they're first neighbors.
Yeah.
Okay.
And the thing is that if these are the main interactions, then and if the system is gapped, if you add perturbatively other interactions, then the phase would remain. It's a bit like, also I should bring this point here, that, of course, we expect the gap to grow with the inverse capacitance. And you see that you already can see something like this happening here, the range of stability. Because if you perturb around the Hadamard couplings, if you're sitting right at CG inverse 0, so what this 3D XY theory is already saying is that, okay, we expect the gap to be 0. Yeah, and indeed, if you don't turn on quantum mechanics, there will be no gap. Like you just have these degenerate states. And then any perturbation away from the Hadamard limit will give you order here, right? And it will be, because you're not stable against perturbations because you're gapless. But as you increase the coupling and you open a larger gap, then you're more stable. You can now perturb around the Hadamard limit here and still has a spin liquid. So it's more robust, and so the larger your gap, the bigger is your range of stability. So the idea would be to first study the pure model with this coupling,
Mm-hmm.
and then actually try to observe if the gap is order J. And if that's the case, then it's safe to perturb. You actually expect also, as you change this coupling here, so suppose like we did, we expand this guy here, and now we can treat this guy as there'll be a W and a W star, and as a function of that phase, when all your couplings become ferromagnetic, you go back to just the XY model. So in this sense, you already have a little glimpse of what the phase diagram hopefully is that if you change your couplings, you get your old XY model. And if you make the, in the special case where you have these Hadamard coupling, that's when you expect your spin liquid in that WXY model.
Okay. I think we have another question from Indarksha. Can the scheme be generalized to non-abelian gauge theories such as SU2 using loop description of the same?
Yeah, we've been thinking about it. We would hope. We haven't had much success yet, but also we haven't tried that hard. There seems to be so much things to do that it is in the back burner. But I would hope, but I don't know. We don't have an answer, a yes or no answer. I would hope yes until you can find that the answer is no. So that's the status.
Maybe we can have other question, anyone? Otherwise, we can stop here.
All right, so if there are
there are more questions. Thank you very much, Claudio, for your talk. It was very nice to have you today.
Oh, you're welcome, and thanks everybody who came.
And hope to see you next week. Thank you very much. Bye-bye.
Bye.